All right, so today we're going to be looking at 8.1, estimating the mean with large samples. And as we've discussed many times, it's really rare that we know the exact value of the population mean. So conclusions about the population can be obtained from sample data by use of statistical estimates. And this chapter introduces you to several widely used methods of estimation. So let's take a look at some vocabulary. An estimate of a population parameter given by a single number is what we call a point estimate. It is a single number used as a best guess. So a best guess for the population mean. We use X bar, the sample mean, as a point estimate for mu, which as you know is the population mean. We use S, lowercase s, as the sample standard deviation as a point estimate for the population standard deviation, sigma. A large sample is defined as a sample where n is greater than or equal to 30. So n represents the number in a sample. The error of estimate is the difference between the point estimate and the true population parameter value. We symbolize the error of estimate as capital E. The reliability of an estimate will be measured by the confidence level denoted by lowercase c. For a confidence level C, the critical value is the number such that the area under the standard normal curve between negative z sub c and positive z sub c equals c. And remember that the area under the curve represents the probability. So let's just make a note here. Area equals probability. And that's a concept that you're already familiar with from previous chapters. Okay, the confidence interval, the probability that our unknown mu, population mean, is exactly equal to the point estimate is virtually zero. To make a more reliable estimate, we form an interval around our point estimate of X bar called a confidence interval. And you'll see what I mean as we do these practice problems. The central limit theorem tells us that if n is greater than or equal to 30, our sample mean will be normally distributed, have a mean equal to the population mean, and have a standard deviation equal to the population standard deviation divided by the square root of n. And here are the steps that we're going to use when we identify a confidence interval for a large sample. So this is the process we will use if we have a large sample. We're going to check that n is greater than or equal to 0. We're going to determine the point estimate, which is X bar, the sample mean. So the point estimate is always going to be equal to whatever X bar is. We're going to determine the sample standard deviation. That will be given. Right, this is given as well. The confidence interval will be given, the level of confidence, I should say. And we're going to determine the appropriate z-score using this table 8-2. Determining the maximal error tolerance for the error of estimate, we'll be using this formula right here. To find the left-hand boundary, we're going to do X bar minus E. To find the right-hand boundary, we're going to do X bar plus E. And then we're going to write a probability statement where we say how sure we are, depending on what the confidence level is, So if we were using a confidence level of 90%, we would say we're 90% sure that the population mean falls between the lower boundary, the left-hand boundary, and the right-hand boundary. All right, we're going to look at practice problem number 1. We're going to do two practice problems together here. As part of a study concerning the effect of physical attractiveness on mental health, a psychologist rated 231 subjects on a scale of 1 to 5, with 1 being highly unattractive and 5 being highly attractive for attractiveness. The sample mean, and let's highlight the key things here, the sample mean was 3.94, excuse me, and the sample standard deviation is 0.75. It says construct a 90% confidence interval for the population mean. All right, so first we have to identify what N is. N is the number of people that were sampled, or the number of items that were sampled. In this case, N is equal to, I should have highlighted that, by the way, N is equal to 231. The point estimate is equal to X bar. The point estimate is X bar, right? So if I ask you for the point estimate, you have to know that I'm asking you for X bar, the sample mean. And I can't stress that enough. The standard deviation here is 0.75. The level of confidence we're being asked for, I should highlight that as well, right, is 90%. So we'll write 0.9. And then we have to look up in the table that I showed you on the previous page what the z-score is for 0.90. So if we go back up to our table, and I'll highlight it, for 0.90, our z-score is 1.645. So we're going to just fill that in, 1.645. The maximum value for the error of estimate, we have to write the formula. Let's go back to where we have it here, right? I have it circled. Z sub c times the standard deviation divided by the square root of n. So I'm going to rewrite the formula. It's always good to rewrite the formula. It just helps you to memorize it. Even though I wouldn't require you to memorize it, I think sometimes it's just nice to know it and not have to always look it up. It just makes things a little easier. We're going to write 1.645, the standard deviation in this case. Now notice we've got our standard deviation for the sample representing our standard deviation for the population. So we're going to write 0.75 here. We're going to use that. And then the square root of n is 231. And you would put that in your calculator, and when you do that, you're going to get approximately 0.08. And I would practice putting this in your calculator, just make sure you're following order of operations. As a matter of fact, maybe I'll do that. I'll open up my calculator. You're going to then calculate the left-hand boundary and the right-hand boundary. Right, you're going to be taking for the left-hand boundary X bar minus C, for the right-hand boundary X bar plus C. All right, let's take a look at our calculator entries here. So what I would do if I was putting this in my calculator, I would do 0.75 divided by the square root of 231. I would do that entry first. And then I would multiply that by 1.645. I don't like to have to type in the parentheses, so I like to do it in stages like that, and you can see I got 0.08. So again, what I was saying was that we have the left bar is going to be X bar minus E. The right-hand boundary is going to be X bar plus E. All right, X bar is 3.94 minus 0.08. The right-hand boundary is 3.94 plus 0.08. Right, 3.94 minus 0.08 is 3.86. and plus 0.08 is 4.02. Right, so let's just highlight these key values here. We need to know this, and we need to know this when we write our probability statement. All right, so we are 90% sure. You could say sure, you could say confident. I'm just going to write confident here. They're interchangeable. We are 90% sure that mu, that our population mean, we can just write mu, is between 3.86 and 4.02. Right? So in this study of attractiveness, if we really want to know what the population mean is, we're going to be 90% sure that people are rating themselves on a scale of 1 to 5 between 3.86 and 4.02, 90% of all people in the population. Now it says form a 95% confidence interval. So we're going to write C equals 0.95. We have to go back to our table 8.2 and we have to look up 95%. All right, so I'm going to highlight that in a different color here. Here's 95%. Here's our z-score of 1.96. So we'll write 1.96. Right, and I'll just make a note here as a reminder. This is from table 8-2. The maximum value for the error of estimate, we're going to use our formula z sub c times the standard deviation over root n. So in this case, for part B, the only thing that's really changing is this. We're still going to have the same standard deviation and the same number in the sample. So we get 1.96 times 0.75 divided by the square root of 231. Right, and you can see that this part is the same. The only thing that's really changed is the z-score. You would put that in your calculator, and we're going to get 0.10. So we now calculate our left-hand boundary, x bar minus e, our right-hand boundary, x bar plus e. So we're going to get 3.94 minus 0.10, 3.94 plus 0.10. And calculate those, we get 3.84 and 4.04. So these are the values we need to write our probability statement and, of course, for 95% confidence interval. We are 95% sure that mu is between 3.84 and 4.04. Now, I want you to notice something very important, that when we were 90% sure, we were between 3.86 and 4.02. When we're 95% sure, that interval got a little wider. We went to 3.84 to 4.04. It's a little bit larger of an interval. So the more sure we are, the wider the interval is going to be, because we are using a higher confidence level. All right, last problem here. I know we have a lot of sports fans in our class, so I wanted to do something related to sports. How old are professional football players? So a random sample of 40 professional football players was taken. Hopefully I got your team in here. I have my team in here, the New York Giants. The mean age in years was determined to be 27.8 x bar and the standard deviation of 3.8. And let us assume that the data are representative of the entire population of professional football players. So we're going to compute an 80% confidence interval for mu, the population mean age of all professional football players. Let's see, we need to highlight that. So n is 40. The number in the sample was 40. The point estimate, which is x bar, is equal to 27.8, and the standard deviation is 3.8. Our confidence interval for this is 80, so 0.8. We go to our table 8-2 and we look up where C is 0.8. And let me circle that. All right, so 1.28. And then we calculate E, Z sub C times the standard deviation over root n. And this S, we're letting that equal our standard deviation for the population. So Z sub C is 1.28 times 3.8 over root 40. And we're going to get approximately 0.77. We have our left-hand boundary and our right-hand boundary. So we're going to have 27.8 minus 0.77 and 27.8 plus 0.77. So we get 27.03 and we get 28.57. We write our probability statement. We are 80% sure, or you could use the word confident, that our population mean, mu, is between 27.03 and 28.57. So what we're saying is the population mean, so the population of all the professional football players, we're 80% sure that those guys are between the ages of 27.03 and 28.57. All right, we're going to calculate now a 99% confidence interval. Let's highlight that. 0.99. We're going to find our z-score in the table for 0.99. Use a different color this time. Let's go with green. Here it is. Oh, I already used that, but that's okay. 2.58. Fill that in right here. We're going to find E, Z sub C times the standard deviation over root n. Now we already have used that in the formula, so that's just going to be the same. So it's going to be 2.58 times 3.8 divided by root 40. We do that in our calculator, we're going to get approximately 1.55. Our left hand is x bar minus E, right hand x bar plus E. All right, so we're going to get 27.8 minus 1.55 and 27.8 plus 1.55. When you use your calculator, you'll come up with 26.25, and here we'll get 29.35. We are 99% sure that the average age of all professional football players, that mu, is between 26.25 and 29.35. So when we were 80% sure, we had a smaller interval, and now that we're 99% sure, we have a slightly wider interval. But we do have a better sense for those ages for our professional football players. All right, so I hope you enjoyed today's lesson. I hope it was helpful, and good luck when you work through the practice. See you next time.